Okay, so today we're going to be looking at the heat of neutralisation. And here's our definition in yellow then. The heat of neutralisation is the heat change when 1 mole of H plus ions from an acid reacts with 1 mole of OH minus ions from a base. And I've underlined 1 mole. Okay, that's going to be very important when we move on to our calculations, that it has to be only 1 mole of, not acid, because acid could be HCl or could be a diprotic acid, which is H2SO4. So there's 2 hydrogens there in the ratio. But it's 1 mole of H plus ions, not 1 mole of acid, okay? So if we have a strong acid and a strong base reacting together to neutralize each other, a strong acid and a strong base by definition are acids and bases that fully dissociate in water. So they're going to fully break up into their H plus or their Cl minus, for example, and all of the ions will be able to react together. So full neutralization reaction will occur. So in that reaction, we're going to get a heat change of around about, usually, minus 57 kilojoules per mole. Now we can also have a weak acid or a weak base reacting as well. So if a weak acid or a weak base is involved in the reaction, that acid or base is not going to fully dissociate within the water. So the neutralization reaction cannot fully take place. So if a weak acid or a weak base is involved, the change in reaction is going to be less than that. So it's going to be around about 52 kilojoules per mole. And that's because the acid and base won't fully dissociate in the water. And if you just notice here that both of them have a minus sign. So for the heat of neutralization, they're going to be exothermic reactions. They're going to be releasing heat into the environment. So I have 2 reactions now written in that contain an acid and a base in the pink. So if we just take a closer look at that, HCl is 1 hydrogen ion reacting with 1 chlorine ion. So we can say that's 1 mole of H plus ions present there. And the same over here, 1 mole of OH minus ions present, which is what we needed from our definition up here. But if we look at the second one, we actually have 2 hydrogen ions and 1 OH ion here. So this is going to contain actually 2 moles of hydrogen ions in this acid. So when we look at our calculations, the very end, we need to make sure to address that if we're actually using a diprotic acid in our neutralization reaction. Because the definition for the heat of neutralization is for only 1 mole of H plus ions. Now when we do these calculations, we're going to use this formula here, which is delta H equals MC delta T. Now the delta stands for the change. So this is going to stand for the change of heat in the reaction. And your answer is going to be usually in joules or sometimes in kilojoules. M stands for the mass of solution. That's your acid and base together. C is the specific heat capacity, which will be given in the question. And delta T is going to be the change in temperature. And that could be in Kelvin or in degrees Celsius, but because it's the change in temperature, it doesn't matter what unit you're giving it in, because the change in degrees Celsius and the change in degrees Kelvin are going to be the exact same thing. So if we look at our first question here, if you want to just pause and read that first, I'm going to take out all of the important information and just create a little table which is easy to look at. So first of all, let's look at the acid. We've HCl and we've NaOH. So they're going to react together. If I do the reaction over here in the corner, HCl plus NaOH, that forms NaCl and a water molecule. Balance it, and there we go. So you can see that it is just a single H, so it's going to be 1 mole of H plus ions that are going to liberate our energy. So let's take out all of the information from HCl and NaOH that we have. We have 250 centimeters cubed of each solution. We have 0.5 moles per litre. That's the molarity for each of them. The original temperature, so the temperature initial was 14.8 degrees Celsius, and the final temperature is 18.2 degrees Celsius. And we need to calculate delta H, so that is what we're looking for. And what other information we're given? We're given that the density of the solution should be taken as 1 gram per centimeters cubed, and the specific heat capacity is 4600 joules, kilojoules, Kelvin to the -1. Okay, so this here, the specific heat capacity, usually gives us a hint of to what we need all of our results, the units of the results to be in. Okay, so if we again remember our formula that we're going to be using is delta H mc delta T. So here, this is the energy. This is the to do with the H, delta H. That's the energy that's released. kg is to do with our mass. So I know I'm going to have to change and convert my mass into kilograms to put it into the actual equation. And delta T is in Kelvin. Here it's given to us in degrees, but again, delta T is the change in temperature. So it doesn't matter what unit it's in at all, because the change in degrees Celsius and the change in Kelvin are going to be the exact same thing. Okay, so I can work out delta T here, the change in temperature, which is going to be 18.2, which is the final. Take away the initial. And that's going to give you a change in temperature of 3.4 degrees Celsius, which is the exact same as 3.4 degrees Kelvin. Now the mass, I don't know the mass, but I know the volume of the total solution once they're both mixed is 250 plus 250 centimeters cubed, which is 500 centimeters cubed. Now I have the density of the solution as well. So when we have the density and volume, we can use the two of them to work out the mass, which is density times the volume. So that's going to be 1 times 500 centimeters cubed, which is 500 grams. Now I already know I need to put into kilograms, so that's going to be 0.5 kilograms for the mass. Now I have everything that I can just use this equation up here. So delta H, the change of heat for this reaction, was 0.5 times the specific heat capacity that we're given in the question, which is 4060. And then the change in temperature is 3.4. Put that all into the calculator, and you're going to get 6,902 joules liberated in reaction. And that is a specific reaction for the amount of liquid that was used. But it asks us to find the heat and neutralisation. So we need to find out how much 1 mole of H plus ions is going to liberate, not just how much was liberated in this specific reaction with 250 centimeters cubed of the acid. So we're going to set up a little, figure out how many moles were actually in this reaction specifically. So I'm just going to wipe this out over here. Now, I only had 250 centimeters cubed of 0.5 moles per litre. So if I had a litre, I would have 0.5 moles of it. However, I only had 250. And we're going to use that relative to what a litre would be and multiply it by 0.5, which is the molarity. Okay, we work that out to be 0.125 moles of HCl that were used in this specific reaction. So 0.125 moles of HCl liberated 6,902 joules. Now, if I want to figure out what 1 mole is going to liberate, I need to divide both sides by 0.125. Both numbers. And that's going to give me 1 mole of HCl liberates 55,216 joules. And if I ask you to convert to kilojoules, this is going to be 55.216 kilojoules of energy released. And that's the answer to that question. Now, this is the second one. So again, if you want to take out the important information, you can pause here. Okay, so I've taken out the information that I think is relevant to the question. So again, we have certain information about the base, certain information about the acid, the temperature change, density of the solution, and specific heat capacity. So, just checking what I have, I need to find out the mass. So I need to convert the volume into mass by using the density. I have the specific heat capacity, and I'm already given the change in temperature this time, so I don't need to work it out. So let's just work out the mass then of the solution. So we have 100 centimeters cubed, of NaOH and 100 centimeters cubed of acid. So 200 centimeters cubed of solution in total. Mass equals density times volume. So the 1 grams per centimeters cubed times 200 is 200 grams. But again, our specific heat capacity is given in kilograms. So we're going to need to change that to 0.2 kilograms before we put it into the actual formula. So now delta H equals the 0.2. Specific heat capacity is 4.2. And it's in kilojoules. You can change that to joules if you want, or you can keep it as kilojoules. And the change is 6.8 degrees. So now, if we put that all into the calculator, we're going to get a delta H to be 5.712 kilojoules. So that's the amount of energy that was released in a specific reaction. So the next step is to just, for clarity's purposes, we can write out the actual equation, what's happening. So we have NaOH and we have sulfuric acid, and that forms these two compounds there. So if you notice, it's now going to be 2 moles of H plus. It's a diprotic acid. So you just need to be careful with that one there towards the very end. So I'm going to figure out how many moles we actually have in this specific reaction. So I only have 100 centimeters cubed, not a litre. So I'm going to have a fraction of the 0.5 moles per litre. I'm going to work that out to be 0.05 moles of H2SO4 were in the reaction. So I can now say 0.05 moles of H2SO4 liberates what I worked out up here, 5.712 kilojoules. I can work out what 1 mole liberates now by dividing both numbers by the 0.05. So 1 mole of H2SO4 liberates 5.712 this much energy. But now, from the very original definition, it's not 1 mole of acid, it's 1 mole of hydrogen ions. So, in 1 mole of H2SO4, we actually have 2 moles of H plus ions. Liberates 114.24 kilojoules because there's 2 ions there present. Okay, so we need to divide this whole line by 2 to get out 1 mole of H plus ions would liberate. And there's your final answer there. That's the heat neutralization calculated for that question.